This is Jarlath O'Neill with the University of Vermont Spatial Analysis Lab, and in this video I'll be covering some basics of high-resolution feature extraction using imagery and LiDAR. I'll make use of a few software packages in this video tutorial, including eCognition, QuickTrain Modeler, and ArcGIS. There are two datasets we'll be using in this tutorial, an orthophoto in Imagine format, and a LiDAR point cloud dataset in LAS format. Let's look at the image dataset within ArcGIS. If we go into the properties, you'll notice that this is a digital orthophoto that has 4 bands associated with it. We're symbolizing it in ArcGIS as a 412 RGB composite, or a color infrared composite. In QuickTrain Modeler, we're going to open up that LAS LiDAR point cloud dataset. This particular LiDAR dataset also has intensity data, so we can toggle on and off the vertex colors. In addition, this LAS file has been classified by the contractor. Of greatest interest to us for feature extraction is the fact that ground points, shown here in green, have been separated from non-ground points. If we go into the properties of the LiDAR dataset, two key factors are of keen interest to us. One, the scale, which is approximately spacing between points, and density, which is the number of points per square unit, in this case square meters. Now we're going to remove the LiDAR point cloud file, and we're going to reload the data as a gridded surface model. We're going to set the grid sampling to a value of 1 for 1 meter, and we're going to the gridding options. Here we're going to click on Help. First, we're going to set our gridding options to create a DEM, or digital elevation model. In order to do this, we'll want to ensure that we're only importing the ground points. By clicking on the classification button, we can go into the LAS filter selection. With the filter using classification checkbox checked, we confirm that the LAS Ground 2 class is selected. We want to make sure that we use all returns, and then we can click Go to import the point cloud into a gridded raster surface model. Now we'll right-click on the model and export it to a GeoTIFF or raster DEM. Now we're going to clear that model, and we're going to repeat that same process. Once again, loading the model as a QTT format, only in this case, instead of generating a DEM, we're going to generate a DSM, or digital surface model. We'll want to set the grid sampling to 1 again, but in the gridding options, we're going to go to the Help, and we're going to follow the recommended profile settings for the DSM. For the DSM, we don't want to sort by classification, but we do want to ensure that we only bring in the first returns. Now we have a true 3D surface representing all features. This is the DSM, so we'll export it to a raster TIFF format as a DSM. Now we'll start up eCognition, ensuring that we're activating it in rule set mode. Within eCognition, please make sure you're in the Develop Rule Sets, or number 4. We'll click on the Create New Project button and choose to import the image data. We're going to give our project a name, and then we're going to double-click on each one of the layers and give them an alias. In this case, Band 1 is red, Band 2 is green, Band 3 is blue, and Band 4 corresponds to near infrared. Giving them aliases will make it easier to work with those layers and also make our rule set more transferable. We're also going to load in the raster DEM that we created and give it the alias DEM, and load in the DSM we created, the digital surface model, and call it DSM. Once again, the DEM represents the bare earth surface, and the DSM represents the 3D surface of all features. Now we're going to edit our layer mixing. We're going to choose to display first the DEM just to make sure the data loaded correctly, and then the DSM. Finally, we'll assign the near-infrared band to the red color gun, the red band to the green color gun, and the green band to the blue color gun to create a color infrared composite. Now we'll begin rule set building. We'll want to right-click in the process tree and click on Append New. The first thing we're going to do is just create a parent process. This is nothing more than a container for all our other rules. We can call this whatever we want, so let's just call it rule set. Now we're going to append another rule. One of the first steps in object-based image analysis is to perform an image segmentation, that is to group pixels together into objects. We're going to use the multi-resolution segmentation algorithm. We're going to create a new level called Level 1, and under the segmentation settings for image layer weights, we're going to choose to not use the DEM and the DSM, and we're going to give the NIR band a value of 2, or a higher weight. We'll set the scale parameter to 30, and then finally weight the shape to 0.3. You can play around with these settings to get the optimal segmentation. But it's important to remember that no segmentation is perfect. Once we've segmented those image objects, we can click on them and see that they have attributes associated with them that appear in the Image Object Information window. We can choose to display additional image objects. In this case, we're displaying both the DEM and the DSM values, and we also chose to display the near-infrared values. So for each object we click on now, we see its mean digital elevation model, mean digital surface model, and mean near-infrared band values. Let's right-click on that rule and slide it under our rule set to fit it under the parent process. Now we're going to add another rule. We're going to do some layer arithmetics. We're going to create a new layer called the Normalized Digital Surface Model, or NDSM. Here we're going to take the DSM and subtract the DEM from it. The Normalized Digital Surface Model is height above ground, and because we're doing math on floating point rasters, we're going to want to make sure the output is also floating point. After we execute that function, you'll see that we have a new layer called the NDSM, or Normalized Digital Surface Model. Once again, this represents the height above ground, and it's a bit more useful than the DEM or the DSM, both of which are relative to sea level. Now we can choose to add the NDSM to our image object information. When we click on each object, we see the NDSM information populated in the Image Object Information window. We can see that features such as buildings are higher than those of ground features. Similarly, we see the same pattern with trees. Thus, the NDSM is a really great way to distinguish tall features from ground features. However, we'd also like to add the Normalized Difference Vegetation Index, or NDVI. We can do that by entering a customized feature in which we take the near-infrared band, subtract the red band, and divide it by the near-infrared band plus the red band. Once we've created NDVI, it automatically appears in the Image Object Information window. When we click on Vegetation, we see that they have very high NDVI values, whereas impervious surfaces generally have low NDVI values. Thus, you can see we have some very easy information to do feature extraction. We've got a combination of height and spectral information. But let's add some other procedures. Here we're going to add a procedure to delete our image object level. This is simply going to allow us to run the rule set from the start and clear out any existing image object levels prior to running the segmentation. And finally, we're going to put the layer arithmetics up top. Now these are preparatory steps, so let's insert another parent process called prep here. And we're going to right-click and slide our existing processes under that prep step. The parent process just allows us to collect our rules all into a single place. Now let's add a secondary parent process called classify. This is where we'll put our rules to classify the image objects. So let's insert a child under this parent process, and we'll use the algorithm assign class. We're going to want to run this only on all those unclassified objects, and we're going to use a very simple condition. Under the layer values, we're going to look at the mean Normalized Digital Surface Model and say anything that has a value of greater than 2 should be assigned to a new class called tall, and we'll make the color for this tall class yellow. Once we click OK, we see that tall now appears in our class hierarchy. And when we execute that rule, we see that all those image objects with a normalized digital surface model value of greater than 2, that is 2 meters or more above ground, are classified to the tall class. So here we've used LiDAR information. Let's append another rule. Once again, we'll use the assign class algorithm. You can access that easily by clicking on the algorithm and pressing A. And we're going to run this only on those existing image objects that are assigned to the class tall. And we're going to use an NDVI threshold of less than 0. And anything that's tall and has an NDVI of less than 0, we're going to assign to a new class we're calling buildings. So once again, these are things that are tall already, but now they have a low NDVI. Let's right-click and execute that rule. We see now that all tall features that have a low NDVI are classified as buildings. However, we've got a little bit of a problem here. And we also see that some water features, which were interpolated incorrectly in the LiDAR datasets we created, have also been classified as buildings. So we might want to slightly rethink our workflow. Our workflow would be much improved if we actually classified water features first. So let's first insert a temporary parent process. And under that, we're going to insert a child process, and we're simply going to use the remove classification algorithm. The remove classification algorithm preserves the image object level but deletes the classification. Now we're going to insert another child process. This is going to be the assign class algorithm again. We're putting it before our other classification algorithms. We're focusing on those unclassified image objects, and we're using a simple threshold here. That threshold is near-infrared values lower than the number of 45, and we're going to assign those to the water class. So all image objects with a near-infrared value of less than 45 are going to be assigned to water. This is being run prior to our algorithm, which assigns those objects that are tall, greater than 2 meters, to the tall class. As a result, we don't have any image objects erroneously classified as buildings in water areas. Now all of our tall remaining features tend to be tree canopy, so we'll just put a simple assign class algorithm here that says anything is tall is now going to be assigned to the class tree canopy. There's no threshold associated with this assign class algorithm. It's really just a reclassification step. We can continue in this workflow by now focusing on the ground features since we've classified all of the tall objects. We can use NDVI once again in a threshold of 0 to assign all the remaining unclassified objects that have low NDVI values to a new class called Other Impervious. These will be roads, parking lots, and driveways. For all the remaining objects, those that have yet to be assigned to a class and are called unclassified, we can assign them to a new class called Other Vegetation. That is to say, all the remaining objects that are vegetation but not tree canopy are now in the Other Vegetation class. This is a pretty decent classification, but if we zoom in, we'll notice that we have problems in some areas, specifically with these buildings adjacent to water. If we turn off the classification, we can see that these aren't buildings at all. Rather, we have some objects with erroneous high normalized digital surface model values that also have low NDVI. But these have some very distinct properties associated with them. First, they have a very high length to width ratio. So let's display length to width in our image object information window. You're going to notice that the length to width ratio of these false buildings is much, much higher than those of our actual buildings. There's another key characteristic, and that's context. The false building that we're looking at here has a high relative border to water features. So we're going to create a new relative border to feature here and display that. You can see that more than 50% of that image object, that is a false building, borders an existing object classified as water. So now we can use an assign class algorithm to go in and focus only on those objects classified as buildings. We're going to use two thresholds. The first threshold is going to say if your relative border to existing water objects is greater than or equal to 0.4, which means 40% of your border is shared by a water feature. The second is going to be geometry related. That is to say that if your length-width ratio is greater than 6. So two criteria here, length-width ratio and relative border to water. Both of those criteria are met, you're now assigned to the water class. So we can see here that using a variety of steps, segmentation, simple classification, and complex classification, we've been able to classify these features. Finally, we're inserting a new process here to export the classification as a raster file. We'll choose the classes that we want to export. Give it an export name, and ensure that we select the option for classification. Now that we've built our rule set, we can execute the entire rule set, and it will run through the segmentation, classification, and export functions, all by clicking on that top parent process rule set and then right-clicking and choosing execute. With our new classification, we can now view it in GIS software packages such as ArcGIS. Finally, we'll want to save our project, and it's also a good idea to right-click and choose Save Rule Set, so you can reuse your rule set again with another project using similar data. That concludes this tutorial. Thanks for watching. Hello, this is Jarlath O'Neil with the University of Vermont, and this presentation is on extracting tree canopy from LiDAR in Definian's developer using the contrast split segmentation algorithm along with some morphological operations. For this presentation, we're going to be working within an existing Definian's developer project. Over on the left here, I have displayed some color infrared aerial imagery acquired at a resolution of 1 meter. This imagery is for reference purposes only. The rule set that you see here does all the feature extraction and morphological operations solely based on the LiDAR data. The LiDAR data that you see here is actually acquired at a higher resolution and with better horizontal accuracy than the aerial imagery. The LiDAR data is a normalized DSM or normalized digital surface model. In a normalized digital surface model, each pixel represents the relative height of features. So that is, the LiDAR data has been corrected relative to the bare earth terrain. My first step is segmentation. In this case, I use the contrast split algorithm. You can notice that you have a bunch of options or parameters in the contrast split algorithm, but I'm going to focus on a few key ones here. The first is the image layer. In this case, I'm using the LiDAR normalized DSM. The contrast split algorithm only works on a single image layer. Now my other settings here, what they say is that I'm using a minimum threshold of 5. So any object taller than 5 feet is going to be assigned as a bright object. And so it's going to be classified in addition to segmented to the class trees. All my dark objects, that is those smaller than 5 feet, are going to be left unclassified. Going to execute the contrast split algorithm here. We'll display the classification over on the left hand side. And link our windows together. You're going to notice that this is a very, very effective process, the contrast split algorithm when used on LiDAR data. You're going to notice a few things that we have to deal with. First of all, we've got some small gaps in the tree canopy here that are probably unrealistic, and we want to close those gaps. And you're also going to notice that we have some spikes in the LiDAR data. That is, we're picking up some tiny features and classifying those as trees. So we're going to want to deal with both of those. That's pretty simple. We can use a remove objects algorithm to take care of that. So in the first one, what I'm going to do here is I'm finding all unclassified objects that are small, and I'm assigning them to the target class of trees. You can see I've removed some of those gaps in the tree canopy. Very similar process to deal with those tiny trees here. That is, I'm removing trees with a small area and assigning them to no class, so they're going to be assigned unclassified. Let's scroll over to an area here where we have some of those small trees and execute that process. What we're left here with are some very good delineation of the tree canopy. The only problem is that due to the quality of the LiDAR, we have some very jagged image objects. And so if we're going to be exporting this data to a shapefile for use in a GIS, we're going to find that the shape of these objects is less than cartographically pleasing. And these jagged edges are most prevalent in these smaller trees. So we're going to go through a series of steps here where I identify those small trees. I'm going to actually grow those image objects by performing a chessboard segmentation around them, and I'm then going to perform some morphological operations using a circular filter to smooth out the edges. So first here I'm going to use a assign class algorithm to simply identify those small trees. You see those here classified and displayed in yellow. And now I'm going to begin the process of segmenting those areas surrounding the trees with a chessboard segmentation. And I'm going to do this through 2 iterations to grow these tree canopy objects out into the surrounding pixels. So first here I'm segmenting unclassified objects using the chessboard segmentation at a relatively coarse scale, a scale of 10. I can execute those. Let's go ahead over in the left hand side here and display those image objects. You can see them there. In my next step, I'm going to classify these image objects into a temporary class, this temp1 class down here, if they border the small trees. And I'm just doing that using the assign class algorithm. Now, it wouldn't do me much good to grow the small trees into these objects because they're too coarse, so I'm going to perform another chessboard segmentation here. And this time I'm going to do it at a much finer scale, only within those current objects that are classified to that temp1 class. The reason why I'm going to do this second chessboard segmentation at a fine scale and not do the original one at a fine scale is that it dramatically improves performance if I can do finer scale segmentations for smaller areas. So now I'm going to do another chessboard segmentation here, only within that temp1 class at a much smaller object size. You can see those smaller chessboard objects there. I'm then going to classify, as I did before, those objects that border the trees into a new class that I'm calling temp2 using the assign class algorithm. Now that those objects are identified, I can go ahead and get rid of all the other temp1 objects that don't border a small tree object, and so I can use the assign class algorithm to reassign those to the unclassified class. I then can merge those unclassified objects back into the larger unclassified objects so that I don't have excess objects. Now I'm going to start with a growing operation. The first step of that is going to be the grow region algorithm. That is, I'm going to grow small trees into the temp2 objects that are surrounding them. This creates some problems because on occasions I have some unclassified objects in the middle of those small trees. So I'm going to use the remove objects as I did before to remove gaps in tree canopy, once again here only for the small trees class. Now that that's taken care of, I can go ahead and merge these small trees objects so that bordering small tree objects are considered a single contiguous object using the merge region algorithm. Now for some morphological operations. In this case I'm using the open image object operation, and my mask here, so the filter if you will, is a circular filter with a width of 5. In this case the morphology algorithm is going to run this circular filter over only those small tree objects which I've specified in my image object domain, and it's going to assign any features that don't fit within that filter to a temporary class, temp1. So these are going to appear blue. You're going to see here that I've identified those edges there. And so now I can go ahead using the assign class algorithm and get rid of those edges by assigning that temporary class, those objects that are blue, to an unclassified class. I'm going to just do some final operations here. That is, I'm going to merge my unclassified objects again, just to get rid of any excess image objects. And then finally I'm going to assign small trees using the assign class algorithm back to the tree class. The end result here, as you can see, we've got a nice delineation of tree canopy, and because we've applied some morphological operations, those trees appear round, and so they're cartographically pleasing and suitable now for export to our GIS. That concludes this presentation. Please feel free to contact me if you've got any questions.